Right now your hand is resting on something solid. A desk maybe, a phone, your own leg. And it feels completely, absolutely solid. You can feel the hardness of it, you trust it. You would bet your life on the fact that it is there. Now here is something curious. The thing you are touching is almost entirely nothing. Not metaphorically nothing. Not philosophically nothing. I mean, if you took every atom in your hand and you scaled one of them up to the size of a football stadium, the actual matter inside that atom, the stuff that is really there, would be about the size of a marble, rolling around in the center, and everything else would be empty. So the question is, why does the table feel solid? Why does anything feel like anything at all? And when you really push on that question, when you follow it all the way down, it gets very strange, very fast. Let me start somewhere simple. Hold up your hand, look at it. You know that hand is made of atoms, everybody knows that now. It is sort of a famous fact. Atoms are the little building blocks. They are tiny, unimaginably tiny. You could line up about 10 million of them across the width of a human hair. Now for a long time people imagined atoms as little solid balls, tiny billiard balls all packed together. And that picture is, well, it is not quite right, but it is not completely crazy either. It is a start, but here is where it gets interesting. An atom is not a solid ball. An atom has a structure. It has a center, a nucleus, which is very small and very dense, and it has electrons, which sort of, well, I will get to exactly what the electrons are doing in a moment, because that is actually where this whole thing falls apart in the most wonderful way. The nucleus of an atom contains almost all of the atom's mass. Almost everything that is actually there, in terms of weight, is squeezed into this tiny, tiny central point, and surrounding it, out at a very great distance, comparatively speaking, are the electrons. Now keep that word comparatively in your mind, because the distance I am talking about is not just a little bit of empty space. We are talking about something that once you see the actual numbers should make you feel genuinely uneasy about everything you have ever touched. Alright, so how empty are we actually talking about? Here is a way to picture it. The nucleus of a hydrogen atom, the simplest atom there is about 1 femtometer across. That is 10 to the minus 15 meters. The electron orbits at roughly 50,000 femtometers away. So the electron is 50,000 times farther from the nucleus than the nucleus is wide. Now that is a ratio of 50,000 to 1. In terms of volume, you cube that, you get something like 125 billion to 1. The atom is 125 billion times more empty space than it is matter. I remember sitting with this number once, really sitting with it, and I could not make it feel real. I kept trying to find something to compare it to, and someone suggested deep space, and it turns out atoms are actually emptier than the space between galaxies. I mean, the space between galaxies is pretty empty. There might be 1 atom per cubic meter out there, which is astonishing. But inside an atom, the ratio of nothing to something is even more extreme. You are, and I mean this precisely, emptier than the void between stars. Now, a reasonable person at this point says, okay, fine, so atoms have a lot of empty space, but that does not explain why my table feels solid. If everything is mostly nothing, why can I not just push my hand right through the table? That is the exact right question. And the answer is, well, it is not what you might expect. It is not because the solid parts are bumping into each other. It is not like 2 sets of tiny billiard balls colliding. The reason your hand cannot pass through the table has almost nothing to do with matter touching matter at all. And once you understand what is actually happening, the whole picture changes. But here is where it gets really strange. The reason you cannot push your hand through a table is because of something called electromagnetic repulsion. The electrons in the atoms of your hand and the electrons in the atoms of the table are all negatively charged, and like charges repel each other. So what you feel as hardness, as solidity, as the reassuring thump of a table is not matter touching matter at all. It is a force, it is the repulsion between clouds of electrons keeping 2 mostly empty things from occupying the same mostly empty space. Now, wait. Let me make sure this lands properly. Your sense of touch every time you have ever felt anything in your entire life has been electromagnetic force, not contact, not solidity. Force acting at a distance between electrons that are themselves not even things you can point to in space. Because here is where the electrons become very interesting and also very confusing. An electron is not, it is not like a tiny marble sitting at a fixed location. No, an electron exists as what we call a probability cloud. At any given moment, the electron is not located somewhere specific. It is kind of smeared out, occupying a region of space. having a higher probability of being in some places, lower probability in others. And this is not a limitation of our measuring equipment. This is not because we are not looking carefully enough. This is as far as we can tell how nature actually works at this scale. I find this remarkable, I mean genuinely remarkable. You might expect that the deeper you look, the more solid, the more definite things would become, like looking at a photograph with a better lens. But it goes the other way. The closer you look, the less certain everything gets. The more it dissolves into probability and tendency rather than location and fact. So picture this. Your hand, pressing against a table. What is actually happening is two enormous clouds of smeared out probability are interacting. The electrons in both clouds are following the rules of quantum mechanics, which say, essentially, that two electrons with the same quantum state cannot occupy the same region. This is called the Pauli exclusion principle. And it is this rule, this strange bookkeeping rule of quantum mechanics, that is responsible for the feeling of solidity. The hardness you feel is the universe enforcing a kind of mathematical law. Now, I promised you earlier I would explain what the electrons are really doing, and I said to keep it in mind. Here is the payoff. They are not orbiting in the way you might picture, like planets going around the sun. That picture is wrong, and it is a little unfortunate that we teach it that way. They exist in these probability clouds, these orbitals, and the orbital shapes determine almost everything about how atoms bond together, how chemistry works, why salt is salty and fire is hot, and you are you and not a rock. But here is the new open question I want to plant in your mind. The electrons are following rules. Very precise, mathematical rules. And those rules work. They predict everything with extraordinary accuracy. But nobody, and I want to be careful here because this is important, nobody fully understands why those rules are the rules. This is the part where I have to be honest with you. When you ask what an electron actually is, not what it does, not how to calculate its behavior, but what it fundamentally is, the answer from the physicists who know the most about this is genuinely we do not know. We have quantum field theory, which is the most precisely tested scientific theory in history. It predicts the behavior of electrons to something like 12 decimal places. 12. That is like predicting the distance from New York to Los Angeles to within the width of a human hair. The math works perfectly. But the question of what is really happening, what the wave function physically represents, whether the probability cloud is a real thing in the world or just a reflection of our ignorance, whether there is some deeper level of description that would make everything feel solid and real again, that is not settled. It is called the measurement problem, and the interpretation of quantum mechanics, and physicists have been arguing about it for 100 years. Some of the greatest minds in the history of science had strong opinions about it and could not agree. I do not say this to be discouraging, I say it because I think it is the most honest and also the most exciting thing I can tell you. Because it means that when you pressed your hand on your desk this morning, you were interacting with something that we can describe with tremendous precision and model with extraordinary accuracy and predict with almost perfect reliability. And we still do not know at the deepest level what it is. That is not a failure of science. That is science being honest about where it stands. And there is something I find, well, almost beautiful about that. The universe has handed us this interface, this experience of solid things and surfaces and the resistance of matter. And underneath all of it, there is this shimmering, probabilistic, almost ghostly structure that somehow adds up to everything you have ever touched. So the next time you set your coffee cup down on a table, consider what is happening. Two regions of mostly empty space, held apart by electromagnetic force, governed by probability clouds following mathematical rules that nobody fully understands. It feels solid. It is not exactly. It feels like matter touching matter. It is not exactly. And the remarkable thing is, it all works. The table holds the cup, your hand picks it up, everything stays where it is supposed to. The universe is pulling off an extraordinary illusion. Or maybe it is not an illusion at all. Maybe solid is just what the laws of quantum mechanics feel like, from the inside. I keep thinking about that,